Good morning everyone. My name is Varun Kumar and today I am going to present my internship project titled Real-Time EV Dashboard and ADAS Warning System with HCSR04. I completed this project as part of my emertxe embedded system internship. The main aim of this project is to improve vehicle safety by monitoring important EV parameters and providing obstacle detection using an ultrasonic sensor. In this presentation, I will explain the project requirements, tools used, working principle, implementation, and finally demonstrate the project. Project requirement. The main objective of this project is to build real-time dashboard for an electric vehicle. The dashboard continuously monitors vehicle parameters such as speed, battery level, and obstacle distance. And another important objective is to implement an ADAS warning system. ADAS stands for Advanced Driver Assistance System, which helps drivers by providing warning alerts whenever an obstacle is detected. This improves road safety and reduces the chance of accidents. The project should work in real time and display all information clearly to the user. Tools used. To complete this project, different software and hardware tools were used. Embedded C was used to write the microcontroller program. Python was used to develop the graphical EV dashboard. MPLab IDE was used for coding and compiling the program. PixSimLab was used to simulate the embedded hardware instead of using physical components. The hardware components include the HCSR04 ultrasonic sensor, LCD, display, buzzer, and microcontroller. All these tools work together to implement the complete system. System architecture. The project follows a simple architecture. First, the HCSR04 ultrasonic sensor measures the distance between the vehicle and nearby obstacles. Then the sensor sends this information to the microcontroller. The microcontroller processes the data and decides whether the vehicle is in a safe condition or if a warning should be generated. The processed information is then displayed on the EV dashboard, and if necessary, a buzzer alert is activated. This entire process happens continuously in real time. PixSimLab. PixSimLab is an embedded system simulator that allows us to test the project without using actual hardware. It provides virtual components such as switches, LEDs, LCD displays, sensors, and buzzers. This makes it easier to debug and verify the project. During development, we used PixSimLab to observe how the dashboard behaves when different inputs are given. It saves both time and cost because hardware is not required during the initial testing phase.
Hello everyone, my name is Abhilash and today I am going to present my internship project titled Real-Time EV Dashboard. The dashboard displays different EV parameters. These include vehicle speed, battery level, obstacle distance, and warning status. These values are updated continuously so that the driver receives the latest information. Monitoring these parameters helps improve vehicle performance and safety. The dashboard provides a clear view of all important information in one place. HCSR04 working. The HCSR04 is an ultrasonic sensor used for obstacle detection. It works by transmitting ultrasonic sound waves when these waves strike an object. They are reflected back to the sensor. The sensor measures the time taken by the echo to return and calculates the distance using the formula distance equal to speed multiplied by time divided by 2. If the distance becomes too small, the system generates a warning. This sensor is widely used because it is simple, accurate, and cost-effective. ADAS warning system. The ADAS warning system improves driver safety by continuously monitoring the distance between the vehicle and nearby objects. The system divides this distance into different zones. If the obstacle is far away, it is considered safe. As the obstacle gets closer, the system displays warning messages. If the obstacle is very close, it enters the danger zone. And the buzzer alert is activated. This helps driver react quickly and avoid positive collisions. Code flow. The program starts by initializing all peripherals and sensors. Next, it continuously reads the visions from the HC SR0K sensor. The measured value is processed by the microcontroller and based on predefined conditions. The system records whether to display safe or random inputs. Finally, the updated information is shown on the dashboard, and the buzzer is activated whenever the cycle repeats continuously during execution. Python dashboard. The Python application provides the graphical user interface for the EV dashboard. It receives the processed data and displays different parameters such as speed, battery level, obstacle distance, and other messages. The dashboard updates continuously, allowing the driver to monitor the vehicle in real time. Using Python makes the interface interactive and easy to understand. Learning outcomes. During this internship, I gained practical knowledge of embedded C programming, Python programming, sensor interfacing, simulator usage, and debugging techniques. I also learned how real-time embedded systems are designed and tested. This project improved my understanding of ADAS concepts and strengthened my problem solving and implementation skills.
Yeah, hello everyone, myself Anjali. Now I will explain the project structure in STM32 IDE. After creating the project, we organized our project into different source and header files. This makes the project easier to understand, maintain. I will briefly explain the purpose of each file. Yeah, let's see. This is the EV dash. This is the actual file we created for our main project. This is the core, INC and SRC. In this INC we can see ADAS.h, common.h, evcontrol.h, fault main. And now let's see main.c in the SRC. This is the actual code for main. Yeah, now common.h. This is evcontrol.h. This is ultrasonic. Here we use HCSR04 ultrasonic sensor to calculate the distance. This is ultrasonic.c file. This is ADAS.c. And this is ADAS.h. And we also create URTC.c file and UART.h file. Let's see how to create header files. Just right click the INC and next new. To create the header file, just click header file and next give any name to that and next finish. And to create the source file, just right click the SRC, then new and source file. Yeah, this is how to create the source file and header file. Now let's see the any errors are not in this EV dashboard file. Just right click the EV dash and build project. Let's see, there is no errors and no warnings. Let's convert this into binary file. Just right click the EV dash and properties, C or C++ build, and just go to general. Sorry, C or C++ build, just settings and MC or MPU build outputs. Just tick the convert to binder file and then apply and close. And then let's see any errors or not. Right click EV dash, build project. Yeah, there is no errors and warnings. Let's see the connections of EV dash file. Yeah, these are the connections. Yeah, and the clock configuration. Yeah, that's it. Thank you.
Okay, good morning everyone. This is Ashishwari. Now let us execute the file in the Pixel Lab. First, open the main. First, we select the blue pill board. And here IO is selected 8 and CPU MIPS was 31.25. Now load bin. Here we have EV dash dot bin. Let us select and click on open. Here we are having the values of EV ADAS system and EV ADAS status and ADAS values and fault values. Now here we have the different type of components. First one is potentiometer. Here we have connected the potentiometer to the PA0, PA1, PA2 and PA3. PA1 is used for accelerator position and PA1 is for brake position and PA2. SOC is nothing but state of charge and here is motor temperature. This is the potentiometer and here we have virtual terminal and this is used for see the readings and used for debugging. By clicking on here we can see the values. Yeah, here we go. Now we have 3 ultrasonic sensors and the module name is HCSR04. This is used for front, left and right. Here front ultrasonic sensor is connected to the PB0 and PB1 and left ultrasonic sensor to PB2, PB3 and right is for PB4 and PB5. Ultrasonic sensors is used to calculate the distances and wait. Okay, next we have the LEDs, indicator LEDs and we have 4 LEDs here. One is for collision warning indicator and is left blind spot and another one is right blind spot and the fourth one is the yellow indicated the fault and here we 4 connected to PB8, PB9, PB10 and PB11 and here we have buzzer and it it to PC13. And the buzzer will ring when collision is detected. And now see the values here. Okay, here we have speed 9.9, SOC 99.9, torque, motor temperature, range, and drive mode is normal, brake, and here you have front distance, left distance, right distance, and collision alarm fault. Now let us see the here. Now let us change the distances front to 198, and we have here collision and fault both. Now let us see the readings. Here it shows the collision 2 and alarm critical, and here fault also collision. Here we have, and next we keep it to here, and we can see the another fault also. Wait. Okay, but still we have fault, and see what is it fault. Motor overheat, because here the potentiometers were so high, so it shows the motor heat. Now let us reduce, and now the fault was 1, and let us see the blind spots. If it is under 30 centimeters, we can see the left blind spot, and under 30 right blind spot was activated. So these are the readings we can see, and these are the readings. Now we have 0 fault and 0 collisions and all. And now let us see it in the Python dashboard. Now we have to turn next, and here we give EV. Paste it here, Control plus S. Now we can run the code here also. Let us do it. And now okay, now EV dashboard was open. Okay, here is the ADAS dashboard blueprint. Now we can see here speed mode is normal, and speed is 66 kilometers per hour, and brake and all. And here is ADAS bird eye view, and here only we can detect the blind spots and collisions. And if this side pen goes to the under 30 centimeters, we can detect the right blind spot, and when it comes to near to the EV, and we can detect the collision. Let us see. can see the blind spot right side, and here we can see the collision here, and it shows alarm also. And if this side goes to under 30, it shows the blind spot left side. So this is the EV dashboard, and thank you for explaining this project.